Okay, my name is Rahnamaye Rabbani. I'm from the Magnetic Resonance Laboratory of São Paulo University. And the São Paulo University, beside the fact that it's a new university, it was founded in 1934. It is a huge university, probably the biggest university in whole South America. We have 11 campi in different cities in São Paulo. The territorial area is almost 18 million square meter. We have built up of 1 million square meter, 89 units, 42 teaching and research center, 33 center of organized organs and leadership and services, 6 specialized institutes, 4 hospitals, 4 museums, almost 100,000 students, from which 57 are from undergraduate and 27 are postgraduate, and we have 5,000 students, special students. There are almost 6,000 fellows and 16,000 technical administrative publications, and scientific production is almost 30,000, each of them 18,000 is in Brazil, and the 8,000 is abroad. Okay, I won't talk about this thing, just it is showing all that we see during this meeting, that genomics is what can or appears to happen, proteomics is what is making it happens, and what is actually happening is metabolomics, what we are looking for. And then there is a vast variety of techniques to measure from micromolar to femtomolar concentrations, and I think that, and we are concentrating in nuclear magnetic resonance, which in my view is probably the best thing to study the biological systems and the illnesses. In this talk I will talk about the metabolomic profile of murine melanoma studied by anemia. Basically, we studied not the melanoma tumors, but the cells. The cells were produced by non-tumorigenic murine melanocyte lineage, melanomas, and it was submitted to stressful conditions by blocking adherence to the substrate, and expected for a non-tumorigenic immortalized cell line. The great majority of these cells underwent anoics after cultivating melanoma. It's 96 hours. We have only 1,000 surviving after for 1 million cells, which means probably is 1.1% of the surviving cell. Then we can do that several times, and eventually after 4 cycles we have a vast variety of tumorigenic samples, which we use TM1 as for our study. And the objective of this work is apply metabolomic approach in order to evaluate changing glucose metabolism induced by galectin-3 in cell cultivated in different conditions of oxygen tension and glucose level. The reason that we are interested in galectin-3 is I will show shortly. What we did, galectin, this TM1 doesn't express galectin-3, and then we had to transfect these cells, and one of them, TM1, which express galectin-3, and the TM1N3, it was transfected, but it doesn't express galectin-3. And each lineage, this I will call them G2 and N3, were submitted to different conditions of oxygen tension and glucose level. Galectin-3, there are 15 kind of galectin, but galectin-3 is basically most active in tumor, in cancer, and it can have demelarization through the C terminals, or if we have some ligand, carbohydrate ligands, we can have polymerization of galectin. And the reason that we are interested in galectin-3, that galectin-3 is basically involved in all sort of process, cancerogenic process, and depending where it is, it can have different role. As you can see, for instance, the nuclear, if it is nucleus, it can promote apoptosis, while the same galectin, when it is in cytoplasm, is inhibit apoptosis. Then that's the reason that we are interested in galectin, and the group of cancer institute in São Paulo University, they are studying galectin-3, and this study is just one aspect that we are doing. There are a lot of other studies that are being done in the university. Okay, objective of this study is the application of metabolomic approach in order to evaluate change in glucose metabolism induced by galectin-3 in cell cultivated in different conditions of oxygen, tension, and glucose level. We prepared, as I said, two kind of TM1 tumorigenic cells, N and G. Then the first capital letter says if it is G, it's express galectin, and N doesn't express. The second letter says if it is normoxia or hypoxia, and the last letter says if it's a controlled glucose or high level of glucose. And from each sample we had a triplicate samples, and then we got the cells, and the cells were homogenized in 250 microliter of methanol water. And this was, we actually did different sort of extraction, metabolic extraction, but this was the best result that we got in 4 graus centigrades, and sonicated at 4,000 RPM for 20 minutes. Supernatant were lyophilized for 24 hours, and then lyophilized extracts were diluted into 600 microliter of D2O and dumped in 5 millimeters resonance tubes. Instead of mixing the D2O and TSP solution to the sample, we put them in capillary, and the same capillary were used again and again to make sure that our standard is okay, it doesn't change the intensity of TSP. NMR spectra were obtained at 400 megahertz and 21 degree centigrade using selective saturation of water signal. And after analyzing all the samples, we could find 29 peaks in allophatic side of the NMR spectra, and we had to add extra +1 normalized. I will show you why we had to add this extra line. And instead of working for each sample, we used the average of triplicated and use PCA for distinguish the samples. This is a typical NMR spectra from 0.45 to 45, which is aliphatic part of the spectra. And the spectra was the line base was taken, and then all the spectra were integrated, and each peak actually we did 2 normalization. First, we normalized to the area of TSP to make sure that our sensitivity of equipment is not changed, it's the same for all of them. And the second normalization was done by a total area of the spectra to make sure that the variation of the mass doesn't make any difference. And then this done, we could distinguish 29 lines, and we had to add the 30th line just to make sure that all the area of these compounds add to 1, because it was normalized to the mass of the total spectrum. We did skull plot VPCA both for 24 samples or for the average ones, which give basically the same result. And this one shows the PC1 to PC2, and this one is PC1 to PC3. Definitely this is more or statistically more significant than the next one. And as you can see, there is a huge difference between NHH and GHH. In other words, hypoxia, when the cells are under stress, they are different from the rest of the samples. And galactina-3 and NH3, which the one that express galactina and the one that doesn't, are separate from each other. Basically, it is what's done. Then we use the loading probe to distinguish which metabolite are increased and which metabolite are decreased. And after that, we could this is basically what happened in the cell. The increase shows the increase are the comparison arrows metabolic increase of NHH to GHH. In other words, the difference between the sample, the metabolic choline and lactate and creatine, taurine are increased, glutamate are increased in NHH, and then in comparison to GHH. Discussion. As we could see, there is a remarkable separation between GH2 and NH2 cells lines when they are in hypoxia and high glucose. In other words, basically, it seems that galactina-3 is efficient. It works when you have stress. Under normal situation, it doesn't have a big role. And then oxygen tension and glucose level are important conditions. Somehow how they amplify the differences. And then as we could see, the GHH and NHH are separated from each other. Galactina-3 deficiency cells are more glycolytic than those cells that express galactina-3. We reached this conclusion by comparing NHH compared to the GHH that has lactate increased. The cellular growth or proliferation by typically observed in tumors are enhanced because NHH compared to GHH has free choline and phosphocholine and glycerol phosphocholine level increased. The cellular metabolism may be more pro-oxidative for galactina-3 deficient cells in hypoxia and high glucose level when compared with those cells that express galactina-3 in same condition. This we can reach this because NHH compared to GHH has higher level of taurine. limited utilization of glucose and or excessive lipolysis for both cell lines in NCC condition is observed. NNC and GNC compared to NNH, and this has hydroxy butyrate and acetate level increased, and finally it's interesting to observe that this condition of high level oxygen, high level of glucose and low and hypoxia, it's very possible in the real tumors, because the oxygen pressure decline much more rapidly than monosaccharide, and then in the middle of the tumor, it's far from the capillarity. It's possible that you have low hypoxia and high level of glucose. Finally, the result indicate that the galactinotrace may be acting in the process of mitochondrial homeostasis when in hypoxia and higher glucose change the flux of glycolytic pathway, regulating cell proliferation rate, cellular lipolysis, cellular energy storage, and oxidativity. Finally, I would like to thank the group from the São Paulo Cancer Institute, Pedro and Dr. Silvina and Professor Roger, and the physics department. This was in collaboration with them, Antonio and myself, and this work was financially, partly financial by FAPESP, and the NMER experiments were done in Institute of Technological Research by Marta and Claudia. Okay, thank you very much for attention.